Hey guys, okay, so I'm back with another video. I know it's been a while because last week I just had some written words and thoughts because of a big debate tournament. But this week I should be back to actually making a video. So today we're going to be talking about lesson 3.3, which is called the dimension of a subspace of Rn. So reminder, in the last lesson, some things that we talked about were linear relations, redundant, vectors, basis, image, finding, image, finding, kernel, so on and so forth. So that's kind of where we're at, right? So this week, we're going to start off by talking about the idea of the dimension of a subspace of Rn. So we start out with a theorem. Okay. So the first theorem that we're going to begin today with is, so let's imagine that we've got two sets of vectors. First, we've got V1 that goes all the way up through VP, right? And imagine there are little arrows over those V's because, vectors. And then we also have W1 through WQ. Now let's say that V1 through VP are a set of linearly independent vectors of V, right? Then these are, these are the vectors that span V. The vectors span V. The theorem is that Q will be greater than or equal to P. Well, what does that mean? So if we're saying that here's Q, right? And here's P, well, Q is standing in for the vectors that span, and P is standing in for the number of linearly independent vectors. What this means is that, in other words, in terms of the vectors that span a subspace, there are going to be more of them or equal to the number of linearly independent vectors, right? And this makes sense because if we think about a matrix, let's think about any matrix that we start with, right? The columns in that matrix span V, right? But you could also pare them down probably to, not all of them are linearly independent. So you get rid of some of them and, they still span V, right? But the point is that the minimum amount to span V is not necessarily, like the minimum amount to span V is, of course, the number of linearly independent vectors, but you can have more of those vectors and still span V. So how would I explain this? Let's think. Let's say we've got 1, 2, 3, 3, 4, 1, 5, 6, 7. Okay, so here are like 3 vectors, right? Now, I'm not saying this is actually true, but let's pretend that this one is redundant. This one can actually be written as 2 vectors, right? So we end up with 2 vectors. So here before, these 3 also span V, right? But these 2 also span V. So the difference is that these 3, they spanned V, but they weren't linearly independent. These 2 span V, but they are linearly independent. In other words, the number of vectors that span V is either going to be greater than the number of vectors that are linearly independent, or it's going to be equal. This is going to be a really important theorem throughout the rest of the chapter. And they include two proofs. One of them is a little more complicated than I think we need to worry about. So I'm just going to do a little bit of a simpler one. We're going to say V is a plane in R3. Okay. So what we know is that there are at most two linearly independent vectors in V. This you should already understand, but in case you don't, basically it's R3, right? So it's a plane, right? So that means that there are two vectors there are at least two vectors that span it, right? You've got a plane, right? So that's going to be two vectors, right? Because it's not a line, it's two-dimensional. So two vectors, right? Well, that means that you might have two vectors, right? But at most there are two linearly independent vectors because there might be two vectors to span V, but some of these might be redundant, right? So the next thing we need to understand is, like I said, there needs to be at least two vectors to span V, right? So this leads to this saying that Q is either greater than or equal to 2. And then here, another way of writing that is that, I'm sorry, that's not correct. It should be that 2 is greater than or equal to P, right? And here we've got Q is greater than or equal to 2. Well, we've got these two things having to be true, right? Well, the only way that these two things can actually be true at the same time is if we've got this thing. If both of these things are equal to 2, if P equals 2 and if Q equals 2, then in other words, P equals Q. So that's a proof, right? Because it's kind of showing if you've got I apologize, that's incorrect. That's not what I meant to say there. Not that P equals Q. The point is, oops, okay, I'm going to ignore that. So you've got at most two linearly independent vectors in V, right? With 2 being greater than or equal to P, right? And then Q is greater than or equal to 2, right? In other words, so so P is less than or equal to 2, Q is greater than or equal to 2. So if you think about it in that context, with P being less than or equal to 2 and Q being greater than or equal to 2, then that means that Q is going to be greater than or equal to P, right? So in other words, what this proof did is it just took a specific example and found that this relationship of the number of linearly of the number of vectors needed to span V and the number of linearly independent vectors, that relationship still holds water under a specific example, right? Okay. So I'm going to ignore the specific proof that they give because even they admit that it's kind of pointless and not really that helpful. So instead, I'm going to move on to the idea of the number of vectors in a basis. So let's do a really quick review of what a basis is. Basis. The vectors of a subspace that are not redundant. In other words, the non-redundant vectors of the kernel or image, right? Okay. So if we know that that's what basis is, right? The number of vectors in a basis. What this theorem is basically going to talk about is that if you know that a subspace is in R to the something, you know that each basis in that subspace will have the same number of vectors. So I'll write this out. All bases in of a subspace V of Rn consist of the same number of vectors. Let's see what this means, right? This is where we get into the P equals Q thing. That's why I was getting confused. So we're taking two bases. We're gonna say that we've got V1 through VP and W1 through WQ, right? Now, these are both bases of the same V. So first, we can say that vectors V1 through VP are linearly independent. The reason we can say that ties back into our definition of a basis, which I'm actually going to flip back to the specific page that gives us that, just so I can have it completely clear in our mind. So give me a second to flip to that, because I really want us to, it's going to be very important to have a strong understanding of what the basis is, to be able to understand what exactly it is that's happening here, right? So let's see. Where is it? Yes, okay. So the book describes that something forms a basis of V if it both spans V and is linearly independent. So in other words, what we need to know here is that V1 through VP spans V and is linearly independent, and W1 through WQ spans V and is linearly independent. So this, just keep that in mind. So first of all, we're saying that this is linearly independent, right? But then that also means that for W1 through WQ, W1 through WQ spans, right? Well, what do we know about the relationship between spanning vectors and linearly independent vectors? Well, that means that Q is greater than or equal to P. But then, because of the definition of a basis, what we can also say is that V1 through VP are a span, right? And W1 through WQ is the linearly independent vectors. Of course, this then yields the relationship P is greater than or equal to Q. Now, if both of these have to be true, right? Both of these things must be true. We must have that P is greater than or equal to Q, and also that Q is greater than or equal to P. How can we make these two seemingly impossible things work together, right? Well, it lies in that equal to, right? In other words, P has to be equal to Q. P equals Q. So that's your proof. Now let's ground it back in what the point was, right? The point was to prove that every single basis, right, of a subspace is going to have the same number of vectors. So in other words, we have this example, right? And it's in V, right? It's in this certain subspace. And we've just proven that two different bases in this subspace have the same number of vectors and have to have the same number of vectors. So that was the point of that. So talking all about this idea of number of vectors in a basis leads us into dimension. And dimension is really the point of this chapter, and almost the point, I think, of a lot of linear algebra. We're about to get into something called the fundamental theorem of linear algebra. So obviously that's pretty important. But the definition given for dimension is the number of vectors in a basis of V is called the dimension of V. Now, the notation that we're going to want to use for this is And about like that. So the number of vectors in a basis. Again, that's just what we were looking at. We were looking at the numbers of vectors in a basis, right? Now they have a whole thing in the book about how this idea of dimension developed, which is really interesting. And if you're super interested, of course, you could always go look it up, but I'm not gonna spend our time doing it tonight. Okay, instead, I'm gonna move on to talking about, now that we've gotten this strong idea of dimension, we're going to return to the idea of independent vectors and spanning vectors, but this time in regards to image. So let's pretend we've got dimension of V equaling M. Okay, that's something we know from the outset. Firstly, we can find at most M linearly independent vectors in M. Now, of course, this should make sense to us, right? In other words, the most linearly independent vectors that we can find are the basis vectors, right? Because by definition of a basis, right? A basis is, and I'll write this off to the side. Basis vectors are linearly independent, right? So if dimension V describes the number of basis vectors, and basis vectors have to be linearly independent, then the linear independent vectors, they're going to be M of them. Now, what confuses me is the at most. That's something that I've got to ask Dr. Prudham about, because you would think that they always have to equal M, right? That they're always M, linearly independent vectors, based on the definition of a dimension. So I will have to ask Dr. Prudham about that. But in general, the idea that you should be thinking of is that there are most likely less linear independent vectors than in the original matrix that you get, right? And that basis represents the linearly independent vectors. Now, the second thing we have to understand is that there are at least M vectors to span V. Now, this should really make sense because, you've got a basis, right? And those vectors, by definition of basis, still have to span V, right? But if we add more vectors, if we add the redundant vectors back in, that still spans V, right? It's just not necessary to be in there. So, we can prove these two things, which we are going to do. Well, first I should say, they explain next that if M vectors are linearly independent, then they form a basis. And if M vectors in V span V, then they form a basis. In other words, if one of these things is true, the other is too, and the set of vectors forms, let's see. The set of vectors forms a basis. In other words, you don't have to prove both of these things. They're automatic. If one of them's true, the other one's true, which is nice to keep in mind because it makes things simpler. I'm going to quickly prove this theorem. So the proof of the first part, right, is we've got these linearly independent vectors, right? We're going to return to that again. We've got V1 through VP. They're linearly independent. And then we've got W1 through WM being a basis of V. Now, of course, W1 through WM has to span V, right? Now, that means that P will be greater than or equal to M, right? Because here's the number of basis vectors, right? M. M is the number of basis vectors. In other words, the dimension, right? Now the dimension has to be, oh, sorry, this should be less than. I thought that didn't look right. Okay. So the dimension, right? The linearly independent vectors, right? There have to be, there can be less than there are in the dimension or equal to, but there can't be more, right? Because, of course, as we pointed out already, the basis is made up of linearly independent vectors, right? Now, again, this is where I'm still a little bit confused on why it's not equal. You would assume that the idea that there has to be equal linearly independent vectors are the same number as the dimension, right? Because the definition of the basis says that it's linearly, says that the basis is made up of the linearly independent vectors. But again, that is a Dr. Prum question. Really, the thing that you need to be taking away from this is kind of thinking about the idea that span and linear independence are a little bit opposites of each other, in the sense that how they're interacting with dimension, right? The at most and at least kind of thing is really what you should be taking away from this. Now, the part 2 of this proof, pretty simple, but of course we've still got this V1 through Vm in V, right? We have to show, because C, we're trying to prove, right, part C. And part C was saying that if these vectors are linearly independent, then they form a basis, right? So, sorry, give me 1 second to look at this. I have to show the vectors V1 through Vm span V. If V is any vector in V, then the m plus 1 vectors will be linearly dependent, since vectors okay. So we've got V1 through Vm, right, in V. We want to show that V1 through Vm spans V. Why do we want to show that? Well, we've already pointed out that V1 through that V1 through VP is the linearly independent vectors. In other words, what we want to prove is that if we know something, if we know vectors are linearly independent, right? Then, or if we know that there are m linearly independent vectors, right? Then we also know that there are, that they also span V and form a basis. Now, the point that you need to really note here is it's if m vectors are linearly independent, and if m vectors in V span V, right? So in other words, what I'm saying is that if you know that at least m vectors are span V, or at most m vectors are linearly independent, you can't draw the same conclusions, right? Because technically the number of vectors that are linearly independent and the number of vectors that form the basis could be, that are span V could be different, right? So it has to be, for this to be true, for us to be able to assume, to make this assumption, we have to know that there are m linearly independent vectors, or there are m vectors that span V, right? So that's what we're trying to prove here. So going back to the proof, we've got V1 through Vm, right, spanning V. And we already proved that the V vector are linearly independent, right? So, like, we already know that these are linearly independent. We need to figure out that V1 through Vm spans V. So if V is any vector in V, then the m plus 1 vectors V1 through VMV, right? We're including this new V. We have added this in to the mix, right? So if we've got this going on here, then these will be linearly dependent, right? Because these vectors are linearly because vectors v1 through vm equals linearly independent, right? Or in other words, non-redundant. That means that vector v, right? Vector v equals redundant in the list of v1 to vm. Meaning, right, based on what we know about redundant vectors, v is a linear combination of v1 through vm, all right? Because we know that v equals an arbitrary vector in v. If we know that v1 through vm is a linear combination that leads to this arbitrary vector, any arbitrary vector in v, we have proved that v1 through vm spans v. Now that was a lot. So I'm going to break it down for us again, right? So the point was we were trying to prove that if we know that we have m linearly independent vectors in v, we can prove that they form a basis of v because we can prove from that they also span v, that m vectors span v, right? So the way that we did that is we took an arbitrary vector, right, in v, and we proved that v1 through vm, these linearly independent vectors, spanned that an arbitrary vector, right? And of course, an arbitrary vector in v, that means that those vectors v1 through vm span v in general. And so knowing that v1 through vm was both linearly independent and now that it spans v, we can say that it forms a basis. So, and of course, you know, it's kind of like vice versa. If you know that something, if m vectors in v span v, you can also prove that m vectors in v are linearly independent and form a basis. So that's the point of that. It's just kind of proving why we can make that sort of large assumption. So the next thing that I'm going to do is talk about finding the base of kernel and image. So we're going to use this method. We're going to use the reduced row echelon form method for both image and kernel. So we're going to start out with this matrix. A equals 1, -1, 4, 3, 2, -2, 8, 6, 2, -1, 5, 1, -5, 1, -8, 5, sorry, this is kind of a big one, y'all, 6, -1, 9, -7. So we've got this matrix. We want to find both the basis of the kernel and the basis of the image. And the very first thing that we're going to do is we're going to change this into the reduced row echelon form. So I'm going to completely clear this for the sake of room. And I'm going to say that we're going to call B the reduced row echelon form of this. What you end up with is 1, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0, 3, -4, 0, 0, -4, 5, 0, 0. Now from here, finding the kernel should be simple because that's how we found the kernel for, you know, the last, you know, couple of chapters. And so I won't go through the whole process, but basically you end up with -2, 1, 0, 0, 0, comma, -3, 0, 4, 1, 0. You know, I wonder if I can make this draw smaller. Oh, here we go. I think I did it. Yay, I did. Okay. 4, 0, negative 5, 0, 1. This is the kernel. Okay. So I didn't really go over that because it's just the same way we found the kernel every other time. And we know that there's no, like, these three vectors are non-redundant. You can go through it if you want to, but you can use that zero method, right? That we kind of talked about, where you look at these zeros between, across the three vectors. And if, something that used to be a zero becomes a non-zero, then that's kind of proves that it's linearly independent, so on, so forth. The point is, these three are linearly independent. So that is our kernel. Now, if we wanted to find image, we've been accustomed to, mostly going from the columns non in the REF form and just taking those columns, and that's your image, unless there's some redundant vectors. Now here, we're going to stay in the RREF, stay in reduced row echelon form for the image. Slightly different than we've been doing it. Now, we need to figure out the redundant columns of A, right? Redundant columns of the original matrix, right? Well, here's the interesting thing that we can do. So let's look at the redundant columns of B. Redundant columns of B, or in other words, the RREF version, right? So that would be B2 is equal to 2B1, and then B4 is equal to 3B1 minus 4B3, and finally B5 is equal to negative 4B1 plus 5B3. Okay. So I'm going to highlight this because it'll obviously become important. Right, here's our redundant columns, but they're the reduced row echelon form redundant columns. So here's the interesting thing. The redundant columns of A correspond to the redundant columns of B. Redundant columns of A correspond to redundant columns of B. Now you can check this if you want, right? You can go back and compare and look at the original vector and, compare these things, right? But you don't have to, because I'm just telling you it's true. You can go back and check it if you want. But in other words, when we say that a column in B is redundant, that means that same column number in A is also redundant. So now that we know that, we have, for example, done B5 equals negative 4B1 plus 5B3, right? So we can create a relationship out of this. But the very key observation here is that we can, at the same time, if we say that 4B1 minus 5B3 plus B5 equals 0, right? We're also saying that for A1 minus 5A3 plus A5 equals 0. So what do I mean by this? So, we took that B5 equals negative 4B1 plus 5B3, right? If we wanted to make that a linear relation, right, what would we say? We would say B5 equals, nope, that's not right. We would say 4B1 minus 5B3 plus B5 equals 0. Now, because we've got the same relationship going on between RREF and the normal, we can also say 4A1 minus 5A3 plus A5 equals 0. And now I'm using B versus A, right, to represent those matrices, right? This right here is referring back to this, and this right here is referring back to our original matrix. In other words, the relationships are the same, right? Whether you're looking at the reduced row echelon form version or the original version. So in other words, we can rewrite all of those redundant relationships that I just pointed out with A. And you end up with the same, like you move all of these things over, right? You turn all these things into A's, you move them all over to make your linear relations, and you end up with the exact same, vectors in the image, whether you're working off of A or whether you're working off of B. So I'll just go ahead and write these right here. What you end up with, 1, -1, 4, 3, 2, -1, 5, 1. But of course, the key point being here that if you started from here and found the relationships, it would be the exact same as if you started from the original and found the relationships and made the image. They come up with the same exact vectors. So I'm going to clear all of these drawings. Now, this may seem kind of pointless because you're like, okay, what does it matter? I use RREF or I use the original. I mean, it's just as easy to use the original. Well, this is somewhat true. However, this leads us into another theorem. So first I'm going to type up this theorem, right? So the theorem is called using the RREF to construct a, that is not right, to construct a basis of the image, right? So, this theorem takes what we said a little bit further. It explains, first of all, why it can be easier to use RREF. So remember, in A, right, that was our original matrix, to find the redundant vectors, you have to go through a whole process. I know that's not fancy math words, but you know what I'm talking about. You have to inspect the vectors and you have to look for the zero rules and you have to, if nothing else, set up a whole matrix trying to figure out if these things are linear combinations of the other things. Well, you don't have to do that with RREF. Instead, you pick the column vectors of A that correspond to the columns of RRFA containing the leading, right? So, right, sorry, got off track here for a second, but what I'm referring to here is we look at our reduced row echelon form, right? And we look at the column vectors. And if the column vector has a leading 1, right, then you pick the column vector of A, the original, that corresponds to that leading 1. And that becomes, that becomes your image, right? Let's see. Sorry, I'm getting a little bit off track here. Actually, I think I'm going to go ahead and stop the video right here because there's a good bit left of the lesson plan, right, that I need to figure out how to review really quickly before I give the second part of this video. So in other words, we stopped right here. We stopped talking about the reduced row echelon form and using it to find basis, and I'll come back and finish up the chapter after I've had a second to look over what I'm about to say.